Yes, good evening, all. Mm, so, I think we have done everything related to body plot, right? All the theory part is ready with us. Now, just we want to apply the knowledge. Whatever we have learned, now we want to solve a numerical. By drawing the body plot, we'll try to get the phase margin, gain margin, right? Stability related what we can say, characteristics of your system. Okay, so I'll take one numerical, and even if you'll do one numerical, that is more than sufficient. You will have idea of how to solve a body plot, a numerical by body plot, right? So I'll write numerical. And I think now it is very much clear in your mind that individual components, whatever they are, right? uh, for your system, right? Like gain or pole at origin, or zero at origin, or real pole, or real zero, or complex pole. So what is going to be the nature of the body plot? It's very much clear in our mind right now. So uh, instead of saying this, I'll write for the given system, for given control system, GH of S is equal to 10 upon S plus 1 and S plus 10. Okay, determine the stability of the system. Stability of the system by plotting body plot, by plotting body plot get, or instead of get I'll put calculate or determine phase margin and gain margin. Okay, wait. And we'll go for the solution now. Just observe the transfer function which is given. What it is having? It is having gain, right? It is having one pole at origin, one real pole, one more real pole is there, right? So the same thing, if I want to write, I can write it as GH of S is equal to I can write this as 1 upon, okay, S 1 plus S and divided by 10. So it will be 1 plus S by 10. 10 divided by 10 and S divided by 10. So we are trying to get these things in the form 1 plus J omega by omega naught, for which we were interested in. If you can remember the thing which we had solved, we were interested in the cutoff frequency over there. Okay? The same thing we are trying to achieve it over here. then we'll go for the next thing, that is we'll write this uh, we'll try to write this thing in S is equal to j omega terms. So I'll write gh j omega is equal to 1 upon S is j omega, then 1 plus j omega upon omega naught, which is equal to 1. Okay, I'll not write omega naught, I'll just write 1. So it's very much clear that first cutoff frequency is 1. And for this one, it will be 1 plus s upon, j omega upon j, j upon omega upon 10. So second cutoff frequency is 10 for this factor. Okay. Yeah. Then the next thing that we want to do is the three factors that the system is having. So I'll write it as 1 upon j omega into 1 upon 1 upon 1 plus j omega upon 1 and 1 upon 1 plus j upon omega by 10. Clear, right? So this one is pole at origin. Otherwise I'll write on that side, that will be better. 1 upon so 1 upon j omega is a pole at origin. Then 1 upon 1 plus j omega upon 1 is a first order pole or real pole with omega naught equal to 1. Okay. And the second one, I'll remove this. Yeah, and again I'll draw. Yeah, and it is 1 upon 1 plus j omega upon 10, correct? Where this is also a real pole with omega naught is equal to 10. Alright, so we'll prepare the table of the factors. It becomes easy if we'll go by the factors, and then collectively if we'll write all the preparing the table for the magnitude and phase, right? So see, let me draw a table. Three factors are there, so this one will be sufficient. The factor and the magnitude and the angle. So yeah, see now. So factor, magnitude, and phase, correct? So our first factor is 1 upon j omega. Now for 1 upon j omega, which is a straight line, which is a straight line, right? And it is with slope minus 20 per dB per decade. And the second thing is it is minus 20 because it's a pole, right? And it is going to pass through omega is equal to 1 and 0 dB ka line, right? So I'll write it over here. So you are going to have slope minus 20 dB per decade, correct? And passing through omega is equal to 1 and the dB is 0 dB point, right? And phi we know that, yes, for that phi is equal to 90 degrees, minus 90, because it's a pole for all values of omega, so no need to worry, correct? Okay, so we have done with one factor. And the second factor is 1 upon C, 1 plus j omega upon 1, correct? So omega naught is 1. I have already written it over here, right? Second thing is, when your omega is less than 1, okay, less than 1 means omega is less than omega naught, correct? Very far away on the left hand side. In that case, the gain is 0 dB. So 0 dB per decade. Okay, and it is going to be when omega is greater than this, greater than 1, that is omega naught. In that case, the slope becomes minus 20 dB per decade, correct? And in that case, the formula for this thing phi is, it is minus tan inverse of omega upon 1, that is omega only. In this case, it will be just omega, correct? Yeah. Then we'll go for the third factor. Yeah. So the third factor that we are having is 1 plus j upon 10, right? So omega naught is 10. That means 0 dB per decade when omega is less than 10, and when omega is greater than 10, correct, it is going to be minus 20 dB per decade. And in this case, phi is going to be minus tan inverse of omega by 10. Okay, so now see, this is going to cut the thing at omega equal to 1, right? This factor ka omega naught is 1, right? So in initial stages, definitely till omega equal to 1, what we are going to have, see, this is also omega equal to 1, this is also omega equal to 1. This line is going to be like this, first part I'm saying, and it is going to pass through omega equal to 1, right? For this factor, omega equal to 1 and 0 dB for lesser values than this, that means it is going to be this. But as soon as it is more than that, this is also having slope in this direction only. So definitely minus 20, this is going to add, correct? Now see the third factor, omega equal to 10. So I'll write this thing as omega equal to 10, let us see. correct. Now again it is still omega equal to 10. This is also having 0, correct. But as soon as it is omega equal to 10, from this point onwards, now you will find, yes, this is also having minus 20 dB ka addition, correct, for this frequency onward. So over here it will be minus 20 dB, and again because of this, and minus 20 dB because of this, so this is going to be 40 dB addition of these two. And this point onwards, this 20, this 20 and third 20, matlab this 20, this 20 and this 20 also. So the slope is going to be minus 60 dB per decade, correct. And so we'll try to draw the graph, the fair one, but just I'm trying to explain you. Now see, this is the critical point and this is the critical point. So on the Bode plot, definitely these two factors should be included. Now before this, how much you want to start, either you can start with 0.1 or 0.01 is your choice, correct, just to have the clearance. But these 2 points definitely should be there on the Bode plot, right? So if you want, otherwise I think it is very much clear. I'll add on this side only, instead of writing again separately for all the points, that I'll add it over here. See, for this factor, the slope we have written minus 20 dB. Let us say, we'll say start at 0.01, okay, and this will end at omega, and will end at 1, correct, 20 dB, only 20 dB I'm saying. After 1, this minus 20 will also get added, so it will start at 1, right, and this will end on 10, right. For these two things, slope is minus 20 dB. These two things means in between these two, from 1 to 10 it is going to be minus 40, because these two things are getting added up, correct. Now this thing will start at 10, and will go till infinity, whatever you want. So jitna possible apne graph pe will try to draw. So ideally speaking, infinity. This is also ideally, it can be anywhere before whatever will be possible on the paper, and this is going to be minus 60 dB per decade. I think it's very much clear, right? I thought, okay, let it be. Then one more important thing is, we should know the just a minute. Yeah, Bode plot I'll draw on the next slide. Okay. So now we want to see, we did this thing for magnitude soil, right? Magnitude plot. Fine. Now I'll go for phase plot. Okay. So we'll go for the individual components. Let me 1, 2, 3, 4, 5. Yes. Okay. So see, now when you are talking about phase, we'll vary the omega and we'll try to see what is the effect on the individual components and then the overall thing. Okay, we are starting at 0.01. So 0.01, 0.1, 1. Okay. Otherwise I'll write in terms of 10 raised to minus 2, so will be easy for us to plot. 10 raised to minus 1, 10 raised to 0, 10 raised to 1, 10 raised to 2. I think this is sufficient till 10 raised to 2. Okay, we'll go till 10 raised to 3. Fine. Okay. Then the first component is 90 only, so no need to worry. I'll write minus 90. So we'll get added with every component. Second one is tan inverse of omega. And third one is, sorry, minus tan inverse of omega. I'm not able to write it. Wait, I'll write it again. Minus tan inverse of omega and minus tan inverse of omega by 10. And then finally we'll add all these angles, whatever will be the sign, algebraic sum, and we'll try to see. So one thing is clear, whatever might be omega, this is not going to change. So this is minus 90 only. And at initial stages means till 1, right? This contribution is 90. Contribution of this thing is 0 because 0 phase hota hai. And contribution of this is also 0. So initially, definitely, initially means I'm talking slightly more than 0, right? So initially it is going to be 90. Okay. And as you'll keep on increasing, now this is tan inverse of omega. Omega is becoming very high. So this will tend towards minus 90. This will also tend towards minus 90. So range of phase. So phi ka range is going to be from minus 90 to minus 270. I think it is clear. And initially 0 contribution. Finally 90 ka contribution. It is going to be highest. Initially it is just a flat, it's a straight line, we know, right? It is 0 dB per decade, and angle is also initially 0 if you have seen the all the factors carefully, correct? Yeah, so now you have to just put this value as omega tan inverse of 10 raised to minus 2. So I am having the values, I'll write those values over here. So this is coming out to be minus 0.57, minus 5, then minus 45. Yeah, we know this thing, right? For this 45 you are going to get when it is becoming that particular what we can say, break frequency, correct? So 10 raised to minus 1, 10 raised to minus 1, sorry, 10 raised to 0, 10 raised to 0 means 1. So at 1 the break frequency is coming for the second factor, this one, correct? So you are going to get minus 45 at that point. Then minus 84.28, then minus 89.4 and minus 89.94. Right? No need to worry for this. Again, one more thing is clear. For this omega naught is 10. So 10 means this. So I should get minus 45 at this point. Rest of the values definitely I'll write. Just trying to explain you the thing. Whatever we have learned, how we can apply and can check whatever we have done is correct or not. No need to calculate these values because 101% it is shifted by 1. Minus 89.4. Okay, so if you add, you are going to get minus 90.27, then minus 95 upon 57, minus 140, minus 219.28, minus 263.68, and minus 269.3439. Done. So we'll use this knowledge, and now we'll try to draw the this thing, body plot. Let me save this. Yeah, and I'll take that image of the body plot first. Just a minute. Yeah, I think it is sufficient. Correct. Okay. So now we have to decide. Once one of the student from Div 1 asked how you are deciding the frequency range, right? So now it's very much clear. We know that first breaking cutoff frequency is 1, right? We want to show the initial condition now, condition also. Now it depends upon you how much you can show in your paper. Those many frequencies you can take, but the critical points definitely should be included. And this is minus 90 to 270. So I think we'll get fitted over here. Yeah, so I'll say omega. Alright, now what we want on the body plot, we want 60 dB tak we want, right? So 3 markings should be there, so I'll try to mark that first. This is 0 dB, so I think I should shift this axis, will be better. This is omega, this is 0 dB. Okay, then 1 2 3 4 5, so I'll say 20 dB. Then 1 2 3 4 5, 40 dB minus 40 dB, correct? And 1 2 3 4 5, so minus 60 dB. On this side 1 2 3 4 5, so 20 dB. Yeah, then I'm marking the this thing, frequencies. So if I'll say 10 raised to this will be better. This is 1, that means 10 raised to 0, 10 raised to 1. So I'll have 10 raised to minus 1 and 10 raised to minus 2. So it is getting fitted over here. -10 to -2. Okay, correct. Then passing through this point of the magnitude, the rate, I'll say minus 20 dB per decade. That means I'll mark the point. It should pass through this, and over here it should pass through this point. Fine. So I'll draw line passing through these 2 points initially. Yeah. Okay. Slope of this is minus 20 dB per decade. And very much clear, rest 2 components are on flat now. At this point, this rate is also there, and rate because of the second component, that is 1 upon 1 plus j omega, that is also there. So now the change will be 40 dB per decade till this point. So now minus 40, that means it is coming over here, and yeah, and this is the point. So I'll draw with different color, so it will be easy for you to understand, right? Yeah, so I'll draw a line from this point till this point, and very much clear. Yes, change of 40 dB is there between these two things. So I'll write over here, now the slope is becoming minus 40 dB per decade. Clear, right? Now after adding this point, this will also have 20 dB ka slope. So now what is going to happen? 20 because of this, 20 because of this, and 20 because of the third component. So it is going to become 60 now. So let me draw it. See, 60 is this. Correct? And now from this point, it should be with 60 dB ka slope, right? It should have. So per decade 60, that means actually from this point till this point you should have change of 60. So yeah, slope should still increase. So let me see now. 1, because it was 0 at this point, it was easy for me, but now we are on 40, so and I have to draw with 60. So it is going to be 1, 1, 2, 3. Otherwise I'll draw a line from this at 60 dB, right, of 60 dB, and parallel to that I'll draw the line. So see, from this point till this point, correct, if I draw a line, that will be off slope. So actually when you will draw it, you do this thing. Correct? Do you agree this line is having slope of 60, minus 60, 0 to minus 60, and in 1 decade this is. So what you are supposed to do now, you draw a line parallel to this. So put your roller on this, right, and shift on this side. Otherwise what you have to do, minus 40 say 60 dB down, that means 100 dB pe you have to go locate the point, because this point will not be useful, right, because it is not starting at 0, so it becomes difficult. Isliye starting to 0 I have drawn one line, right? Either you draw a parallel line to this, okay, otherwise the another way. I am doing both the things, so will be easy for you. We are over here, right? This is 60, so 1, 2, 3, 4, 5. So this is going to be 80. 1, 2, 3, 4, 5. So down 1. And here. Correct? So if I'll draw this line, you can see that yes, it is parallel with this, definitely. So I'll not draw the whole thing. I'll just draw for one. For how many this thing we had considered it? Achha, infinity we had written, but 10 raised to 3 will be too much. So I'll just go like this. Okay, so these 3 things, 1, 2 and 3 are giving you, let me shift this line, so I'll be able to locate 270 and 90 on it. So what I'll do is, I'll shift this line. Let me see. If not possible, then definitely we'll try to reduce this line. Yeah, I'll remove this. Okay, even I can do one more thing. I can just locate one of the point over here. Alright, I'll remove this line. Yeah, and I'll draw only till this point. So will be the thing will get fitted on this particular Bode plot. Yeah, I think it's okay now. Correct, and I'll write over here. So yeah, and this is minus 60 dB per decade. Okay. Now we are going for the phase. Phase is starting at 90 and it is going to end on 270. So let me see now how we can fit it. If I'm saying this thing is okay, minus 90, then 1 2 3 4 5, let us say this is minus 180, 1 2 3 4 5, so this is going to be minus 270. So we have to fit it in between these two. Now 90 degrees for 5 divisions, right? That means 90 divided by 5. So per division is of 18. Very difficult to draw, but let us see how we can fit it. Or we can have some more. No, not possible. At least not possible over here. If you are with the actual hard graph paper, no, matlab semi-log paper, I think it will be easy for you to draw. Okay, let it be. Let us try to fit the thing. Hai. So I'll mark the points, and the points are when your omega is 0.01, that means this thing, right? This thing, the angle is minus 90.6. Minus 90.6, so somewhere over here. Okay. Then the next one is, I'll draw for 1 mainly. 1 means 10 raised to 0. For 10 raised to 0, it is 140. So, what I said? Yeah, 4 divisions. 90, 18 into 4. And plus 90. So, how much it is coming out to be? 162. So, this line is for 162. Okay. You want 140. Just a minute. So 162 minus 18. So 144. Okay, and we got 140. That means near about 2 divisions. Alright, 10 raised to 0. That is 1. And this is 142. So slightly above that. I'm trying to mark. Okay. I think you got what I'm saying. 90 to 180, 90 degrees. Correct. 90 divided by 5 I have done. So it 1 division it is coming to be 18. So I try to calculate what is coming 140, where it will come, where it is going to locate. Okay. Then another critical point that we are having is 10 raised to 1. For 10 raised to 1, the angle is 219. So 219 means we can say 220, right? So 180 plus 18, 198 plus 18, 216. Okay, so somewhere on the second division. So over here 180, somewhere over here, and this is 216, so slightly above it. So I'll try to mark the point. Okay. Then rest of the 100 is 263. 270 minus 18. So 252. Okay. So this point is 272. This point is 252. Okay. So in between somewhere. Yeah, I'll mark it over here. Correct? 10 raised to 263, sorry, 263. Just a minute. So 252, so 263 will be somewhere in between. And this point is 10 raised to minus 2. See, for us, what is important? Where this thing is going to cut, and when it is crossing, where it is going to cut. So when you are going to get 180, that is very important. Now, definitely I am supposed to draw freehand. I'll try to draw it. we'll try to see phase margin and gain margin, but if you'll have better scale it will be good, है ना. So now I'll try to just draw it. 90 plus something. Wait, very difficult for me to draw it. Definitely when you will be and you can do the reverse engineering also, try to go for some more points, right, like I have tried for 10 raised to 0 and 10 raised to 1. You go for 10, 20, sorry, 1, 2, 3, 4, 5, right. So if you will consider omega is equal to 5, then you try to find out these angles, so you'll get more accurate. Now you'll get the thing that where it should be. Okay, let it be. Let me see now if I'll draw those lines of PM and GM, what it is going to give. Yeah, and this point it is cutting. Okay, so the next thing is, this is omega GC, correct? And the second point is here where phase is getting crossed, right? That is your omega PC. So I'll write it. This one is omega PC, phase crossover. And we had seen one thing, if you are having omega GC less than omega PC, then your system is stable system. And now let us see when first we'll go for the angle. When gain is crossed, gain is 1, right? You can see that it is above it, that means 180 से angle कम है, right? This part, wait, I'll draw from this point till this point. No, it's not. I'll draw just a straight line. Yeah, this part is telling you this is your GM, PM, phase margin. How much it is, we'll see. But when gain is 1, right, angle is less than 180, definitely your PM is positive. That means your system is stable, correct? Because phi minus 180, and your phi is negative, so definitely you are going to, all these things we had seen in the last lecture. I don't think any need to explain you all these things again, है. Then the next thing is, when phase is getting crossover, you can see that here gain is still has to cross the thing. Gain is not 1, gain is less than that. Here gain will be on higher side, here gain is on the lower side. So again I'll draw. Yeah, so from this point, no, sorry, here, oh, from this point till this point, right? Whatever you are having, this is your GM. And gain is less than 1. If gain is less than 1, then GM is more than 1, and log of GM, definitely more than 1 means it is positive. And if both are positive, yes, system is stable. So I'll write it over here. I'll just write the values. I'll just write the signs. Why I'm writing signs? Because I don't know whatever I had drawn how much correct it is, right? I'm having the actual values on the graph paper, on the semi-log paper. How much correct thing I got, I don't know. So I'll read out whatever values I'm having afterward. But what is important for us over here is, main thing is the signs, right? So I'm saying PM positive, GM is also positive, omega GC, right, is omega gc is less than omega pc. So all these three things are indicating that yes, system is stable. Done. Now see, whatever we got, we'll try to read how many divisions. Two divisions, right? So 180 minus 18 minus 18, 36 HU2. So I got 144 over here. So I'll write it minus 144 degree. Okay. From graph, or I'll say from Bode plot. From Bode plot, drawn over here, I got minus 144 degree. I'll write it. PM is equal to, or I'll write down. PM. Okay, I'll write first 5. 5 I got minus 144. But actually, when I had drawn it on semi-log paper, I got it minus 138. Hard paper, I'll say. This is for you, This is just explanation for you how you can draw it. I am already drawn, but I cannot show you that thing over here. So please draw it and see. Hard semi-log paper. 5 I got minus 138. Still it is very good. The accuracy is okay. So if you are talking about PM is going to be minus 130. I'll take these values. Minus 138 minus 180. So it is coming out to be plus 42. And plus 42, that means system is stable. On the other side, now I would like to measure the gain also. So this is 20, this is 40, and how many divisions? Each division will be of 4, correct? 20 divided by 5, that is 4, correct? And where we are somewhere over here. Yeah, so it will be 24, 25, 26, 27. Okay, so I'll say GM, which I got, is 27 dB. Okay, but the thing which I got from the actual semi-log paper, I got it to be equal to 32 dB. Hard semi-log, I'll write. Again we got a positive value, that means system is stable, right? So this is GM and PM. Omega PC, yes, what I got, omega PC over here, omega PC, that is 10, 1, 2, 3, 1, 2, 3, 4. I got 4 radian per second. Correct? And from the graph paper, I got omega PC is equal to 6 radian per second. This is hard. Don't get confused, please. And then omega GC, what we got over here, omega GC over here, we got exactly 10. Sorry, this one, right? I made a mistake of what? Omega GC and omega PC. Omega PC is over here. So omega PC is omega GC is 1. है ना. Omega GC is 1 and omega PC is yeah, I have written 6. करेक्ट है. सो ओमेगा GC डेफिनेटली इसी पॉइंट पे वो बेंड हो रहा था, तो इट इज गोइंग टू बी 1 radian per second. This is definitely correct because the graph itself is giving you these values. Omega GC is equal to 1 radian per second, and this one I got 6 over here, but in the hard paper, but I got, now we got it to be equal to 4. So I think all the parameters we have found out. So all the best to everyone. Try to go on these lines, right? Try to solve some more numericals. Definitely will be helpful for you to go for the final exam. All the best. I'll save this. Yeah, I'll add to this also. Magnitude plot I have not written, so I'll write. And phase plot. ठीक है? Yeah, now I'll save this. And all the best.